Everyone, in this video, we're going to go over Gauss's law, but we're going to do it for cylinders. Let's begin. So, for the last three videos, we looked at a Gaussian surface for a point charge, or a sphere. So, if we have a charged sphere, we created a Gaussian surface around it, and we did the math for that. We also did a Gaussian surface for a charged plane. Okay. And then we created the Gaussian box for that one. And so for this one, we're going to create a Gaussian cylinder. And for Gaussian cylinder, the simplest thing that we can do is a line of charge, okay? Either a line of charge or a cylinder of charge. So let's begin. So let's say we have a line of charge that looks like this. Okay, so you could think of it like a wire, and let's say this is all positively charged. So this is a line of positively charged objects, or positively charged line. And what we get is a E field that emanates 360. I'm going to try my best at a 360 representation, okay, around, and we also have it behind like this, okay? And this is throughout the entire length of the wire. And so the best way, I guess I'll do one down here as well. So the best way to encapsulate this E field with a Gaussian surface is the Gaussian cylinder. And we'll see that in a little bit there. All right, so the Gaussian cylinder, it makes sure that all the requirements are met. So the requirements are, it's a closed surface. 2, the E field and the area, it either gives you a cosine of 0, which is what we want. So this means we have all the flux, or we have a cosine of 90. And if you remember from the charged plane, we saw that the charged plane, some parts of the box had a cosine of 90, right, where there was no flux. And we'll see that again here today, right? And so these are the two requirements for the Gaussian surface. I'll do this in a different color. Let's try red. So the Gaussian cylinder, okay, is just a cylinder like so. Okay, there we go. And I'll shade this in there. And then we have, that's a Gaussian cylinder. So what we're doing here is the E field is going through all parts of that cylinder equally, and it should remind you a lot of the point charge, but the only difference is that it's not emanating outwards in a 3D fashion, like it's not exploding out, right? The E field is perpendicular to each point along that line. All right, so here we have the Gaussian surface, which is in red, and we have our E field, and there's a couple of points here, okay? I'll call these the caps, right? So these are the caps of the cylinder. So the caps of the cylinder, you'll notice that the caps of the cylinder, it does not have, caps have no flux, okay? So meaning the E field does not go through the caps. So there is no flux through the two end caps of the cylinder. So the flux only occurs within what I'm going to call the body of the cylinder. Okay, so the flux for the body, check. Flux for the caps equals 0. There's no flux. So what we want to do is we want to use Gauss's law to figure out exactly how much flux is going through, or how much E field is going through this line of charge. So, the other thing I want to mention is the charge density. So we have charge density. So we have a brand new one. This is a linear charge density. So this applies for a line of charge. We can say the linear charge density, which is this Greek letter right there, is charge per length, right? Or if we have total charge, it'll be Q over L. If you have a little section of the line, which is what we have, it'll be this version. Alrighty? Okay. So let's actually solve this problem out. For this cylinder, let's say, I'm going to redraw this here. So that's our line of charge. And this is our Gaussian cylinder right there. Okay. Let's say the radius of this Gaussian cylinder, it's going to be just a lowercase r. Remember the Gaussian cylinder, it can be, we can make any shape. So I'm just going to use lowercase r because it's going to be our variable. And we'll say that the length here, the length of this, or the height of the cylinder, for this, I'll just say it's going to be capital L. Okay, that's the length of the cylinder there. All right, so a couple of important things geometrically about this Gaussian cylinder. Because the end caps don't matter, how we can view this cylinder, I guess in terms of a surface area, is we can imagine it as like a piece of paper, right? It's a piece of paper that we rolled up so that it looks like a cylinder. So basically, any part that is a piece of paper has flux going through it. So all parts of the paper. And you'll notice that two end caps here and here, it doesn't have, there's no paper there, and that's because there is no flux going through those two end parts. So the geometric, a little trick that you can do is if we unravel this piece of paper, okay, what we end up with is a rectangle. So that's going to help us out with our dA. So the area that we are concerned about is essentially a rectangle, okay, where this length here, okay, and we'll just call that the height of the cylinder, okay, L, and this part of the cylinder, this is your circumference. This is going to be the circumference of the circle or the cylinder. And that gives us 2 pi r. Okay? All right. And with that, let's go straight into Gauss's law. So the flux is equal to the surface integral of E dot dA, which is equal to the Q enclosed all over epsilon naught. Okay, and epsilon naught does have a value in case they ask you for it in the future. All right, and we know that the E field is uniform, so we're going to pull that out because it's a constant. And the surface integral for our shape here, even though it's a cylinder, it's technically just this rectangle. So we're going to call it 2 pi r capital L, okay, which is equal to Q enclosed over epsilon naught. Okay, so I haven't done anything with the Q enclosed just yet. I'm about to. So this left-hand side, okay, we're good. All right, but let's figure out this right-hand side, this Q enclosed. So I'm going to bracket that off right there. So we know that the linear charge density is the total amount of charge divided by the total length. Here we chose capital L. So I'm just going to write out length here, which is equal to the Q enclosed divided by, in this case, the enclosed length of wire. We foolishly labeled it as capital L, and so we get this ratio here. And so what we get is that the charge density is equal to Q enclosed divided by the length of that cylinder, and so we can replace, right, this is just substitution at this point. We can replace this into our formula, and we get E equals 2 pi, the radius of the Gaussian cylinder, times the length of the wire that it's enclosing, which is equal to the charge density times the length of the Gaussian cylinder divided by epsilon naught. So if the problem is asking you for the E field, okay, the E field that is being covered by this Gaussian surface, we would get E field is equal to all this 2 pi r L epsilon naught, and at this point we get some fancy algebraic magic going on, and I'll show you what I'm canceling out. The L's cancel out, and we're left with this. And those of you with a keen discerning eye will notice that there is a K hidden in there. So if you remember, Coulomb's constant is 1 over 4 pi epsilon naught, right? And so here we can see there's a 2, a pi, and an epsilon naught right there. So what this means is that because it's 2 pi epsilon naught, that is a half of the K. So 1/2 K and divided by R. Okay, and that's just a little fun way of seeing how the Coulomb's constant is still within this problem. All right, and that's it. Okay, I'll see you next time. Bye bye.